Hi, welcome to Engineering Q Vectors, class number 6. We're going to discuss the AB matrix in this video. The previous video we introduced classical matrices. In this video we're going to discuss the matrix which results from the multiplication of two vectors. This matrix is a special kind of matrix which I euphemistically call an AB matrix. This material does not replace classical matrices, it merely augments it. Okay, and in the early development, if you remember a couple videos back, the way we found out about the AB matrix is that we multiplied three vectors together, A times B times C, and we found out that when we drop the C out, we get a matrix, and that we now call the AB matrix when we get rid of the C. So we found the proper result of multiplying two vectors by multiplying three vectors and then dropping the multiply when we got to the end. We found that the proper result of multiplying two vectors is a matrix. Now if we do this for other dimensions, because I was interesting because when I went to 3 dimensions we found out it's a 4 by 3 matrix. 4 dimensions it comes out to be a 4 by 4 matrix. 5 dimensions comes out to be 8 by 5, all the way down to 8 by 8 multiply is an 8 by 8 matrix. Now this blew my mind. It means that the proper matrices are all 2 to the n dimensions, because I tried extensively to make use of these and they're still missing information. It's when you get to 2 to the n, dimensions of 2 to the n, everything works out fine. If you want to use subsets like this, you end up using the higher set and just use the upper. So if you want to do a 5 by 5 algebra, do it with an 8 by 8 rule set and everything will work out fine. Okay, don't try doing it with working with the square matrices, everything works out better. And I took this all the way up to 16 by 16, so using a computer. Okay, later on I realized that, again, because these are non-conservative, you lose information. You got to use the next dimension up. So use the 2 to the n. And for 2 by 2, you're only going to use the x and y, but you end up using rule sets 4r and 4l. I'll explain what these are in a second. And the 4 by 4 is the one we're predominantly going to stick with. This gives us q, x, y, z as the dimensions. This is also known as cube plus 3, and we use the 4r and the 4l rule sets. There are the rule sets for 16 and 8 by 8 and 16 by 16 have been developed, but these are still under exploration. They don't have any properties beyond the 4 by 4, but it's just I don't have a need for them now, so I didn't really go into exploring them too much. We're just going to focus on the 4 by 4 because that's the one needed for ethereal mechanics, at least right now. So what are the rule sets? Well, this is an example of a rule set. This is the 4R rule set, which is 4 XOR 16, and I'll explain what these numbers mean. 4 means it's 4 dimension, 4 by 4. XOR is how the indexes came out, and 16 is how the signs, the blue squares came out. I'll explain that in a second. What we've done is we've replaced the dimensions with numbers. So 0 is Q, 1 is X, 2 is Y, and Z is 3. And the reason why we did that is we want to be able to use a computer to compute the resultant dimensions. And the way that's done is using the exclusive OR process. So you'll notice that the number, forget the sign, don't worry about the sign, just look at the number. The number is the exclusive OR of the row and the column index. Okay, and that's how you end up with the number. And when I put Q as the first dimension, the exclusive OR worked for everything, including quaternions. It was really amazing. All right, so it's a 4 dimension. The input and output dimensions are computed using exclusive OR by assigning the dimensions an integer number. And 16 is the sign. Well, how do we get 16? Well, if you take the main diagonal and you assign bit numbers to the column, to the elements in the column here. Okay, so this would be 0 for the first one because there's no negative sign. So this is first. The second is a 0 because there's no negative sign. Third is a 0 because it's no negative sign. Fourth, fifth is a 1 because there's a negative sign, and the sixth is a 0 because there's no negative sign. And if you take the binary number of this, you get 16, and that's how the 16 is the pattern of the signs in the upper quadrant, I guess it's called, the upper, I forget what you call it, the upper half beyond the diagonal. The lower half is just the mirror image of the signs. That way there you don't have to encode both sets. Okay, so that's what this stands for, and this was used to help a computer go search through all the bazillions of different types of rule sets it could come up with. 4R means this is a right-hand rule set. There's also 4L, which is 4 XOR, I believe it's 36. And we'll look at that in a minute. Okay, so that's what the blue just highlights, those are the negative signs, so that's easy, so you can look at the pattern. The 4R is just a simplified name from the actual name, computer designated name. And these are the input, and this is in a matrix. The way this rule table works is if you have x times y, you go in x, which is 1, and you go to the y column, and your output is going to be z, which is 3. And because there's no negative sign here, you don't have to negate the answer. Okay, so the negative sign isn't mean as it goes to minus z, it just means you negate the answer. So if x is minus 3 and y is 2, your result here is going to be 5. 3 times 2 is 6, or minus 6. Okay, but if your answer came up minus 3, you'd have to put a minus sign there, which would negate that. So you got to keep track of all the signs. It's kind of convoluted, but that's the way it is. And this is not my invention. This is the way the mathematicians do their rule tables. Okay, let me give you some examples here. Let's say we have a times b times c. And in the previous video where we have ax plus ay, and we multiply that by bx plus by, and we do that first, and then we do cx plus cy, and then we permutate through all of those. Well, I'm just showing you this because we're going to use the Q dimension as well. So these are just certain terms I'm showing you as an example. If these were really 4 by 4 by 4 multiplies, we'd have 64 terms here that we'd have to compute all the results. But let's just look at each of these terms as examples. So x is 1, y is 2. So our output for this guy is 3 without inversion. Okay, now we take this guy, which is now 3, and multiply by y, which is 1, to get 2. That means our output goes to y without inversion. So that would be dy. Okay, the next one we have ax by, which is 3 again, times q. 3 times q, it goes out to z, negative z. See how that works? So whatever value you get for these, so in other words, your magnitude is going to be the a, the b, and the c, or x, y, and q. And then whatever you get from multiplying those together, you negate them, and that goes into dy, or dz rather here. Okay, let's do this one. ay, okay, this is y, which is 2, times x, which is minus 3, so we have a negate already. Okay, and yx is z. Okay, z, which is 3, times y, which is 2. We have another negate, and it goes to y at the output. So there's these two negates cancel, and so you just multiply the 3 coefficients together, and that's going to go to the dy output. Okay, and the same thing, I'm not going to go through these for you, but if your c ends up being multiplied from the left instead of the right, you're going to find out, for example, for this guy, it's going to be a negation of the cxcy and it's going to go to the dy. You're going to get a negative answer. So by swapping your right multiply with a left multiply, you end up negating all of your cross terms. But you can go through that yourself. We're going to show you simplified examples going further. So we have a cornucopia here. There are virtually infinite possible rule sets, some with some very interesting properties. For example, 8-dimensional XOR 160638992 mimics Cayley's 7-dimensional cross product. All you have to do is ignore the Q components. And the Q components of my matrices are the first row, first column, and the main diagonal. Okay, those are the Q components. So if you ignore the Q components, the remaining components match exactly Cayley's 7-dimensional cross product. There's also quaternions. 4 XOR A, 2, 3, 6, 4, 8. And the A is different. A means we're going to do all the bits. So in other words, the way you get this number here, instead of just doing the upper right like we did before, the A means you do them all. So you go down this row, you get 4 zeros, a column, you get 4 zeros, then you get 0, 1, 1, 0, 1, oops, 0, 0, 1, 1, 0, 1, 0, 1. You convert that to binary, you're going to get 23, 6, 48. Okay, so this binary way is where you can just keep incrementing the sign to go search for different rule sets, because they all end up being XOR for the numbers. It's just the difference between them all is just the signs, how the signs come out. Okay, and so, you know, we get the same indices for quaternions that we do for regular vectors, or Q vectors. The difference being is how the signs come out. That's it. And this gets rid of the what's the definition of the cosine, the square root of -1, because now -1 just becomes a direction. And it's a very simple resolution to the old undefined square root of -1. And so what we show here is these tools have the potential to unify all of mathematics and eliminate a lot of the undefined nonsense that still persists. Okay, this is my assertion based on the following progress. We've unified vectors and matrices. Instead of the others out there that say that a matrix or a vector is just a row matrix or a column matrix, which is bullshit from a dimensional standpoint and an algebraic standpoint, we now show that a matrix is a result of multiplication and division of vectors. We've also resolved the missing divide in the erroneous multiply vector. I just said that. But I leave all this unification to others. I have developed this Q-algebra only to the point that I need in order to unify the forces of nature. The paper that I wrote that was submitted shows how to generate the rule sets for any system of 2 to n dimensions, anywhere up, however you want to go. Once you know a basic 4-dimensional, you can use the 4-dimensional to generate the 8 and the 16, and the 16 to do the 32, and the 32 to do the 64, all the way up. And one leads to the next. And the computer search, doing a rough way, found that that solution is the proper solution going back to the original seed matrix. Again, the possibilities are endless. For my purposes, I applied constraints to the computer search to limit the result to my needs. The two results that appeared for 4 dimensions are 4 XOR 16, which is the 4-dimensional right-hand rule, and 4 XOR 36, which is the 4-dimensional left-hand rule, which are here. And the interesting thing is that the only difference between these two matrices is that the Q, for ignoring the Q components, the others just have the signs. The remaining components just have a swap in the signs. That's the only difference between the right-hand and the left-hand rule, which makes sense. All right, from here on forward, the properties, identities, and derivations shown from this point are valid for the 4R rule set only. I'm pretty sure they apply to the 4L rule set, but I have not had time to check. Okay, so the Q-algebra for rule set 4 is what is needed for Ethereal Mechanics, and that's what we will focus on. So let's go look at the AB matrix in a little bit more detail. Remember, we developed the AB matrix, I believe, 2 videos ago. And if you do apply the right-hand rule, which now you're going to be using the 4R rule set instead of the right-hand rule to figure out where all the components go, you find out that the dot product, the classical dot product, appears along the main diagonal, and the classical cross products appear everywhere else. And that's true even when you get to higher dimensional matrices. We have a shorthand notation like that where we show dots and then the appropriate Z normal, which would be the, you know. So what I deduce from this is you can separate this matrix into just the dot products and the remainder, which would just be the cross products. And then we call this the new dot product, which we're going to represent as A dot B in brackets to show that that's a matrix now, and A cross B in brackets to show that that's a matrix as well. So this is the new vector multiply AB, which results in a matrix, is the new dot product, which is a scalar matrix, and the new cross product, which is, I believe it's called a skew symmetric matrix. Okay, so again, just like we demonstrated in the old classical thing that the vector multiply is the sum of the cross and the dot product, but now everything's in matrix world. And because this is a scalar matrix, and scalar matrix has interesting properties in Q-algebra where you can show it as a plain scalar or in its matrix form, it's interchangeable. Because whether you take the scalar like we showed before times the vector A or the scalar matrix times A, it's going to end up to be the same result. So the new dot product you can show either way. The difference is when you need to add the new dot product to another matrix, you have to do it in matrix form. It's only when you multiply that you can have a scalar matrix shown as a regular scalar or as a scalar matrix, you get the same result. So that's why it's important that we realize that this is really a scalar matrix. Because when it comes down to adding this matrix to another matrix, it has to be in matrix form. You can't add the scalar to a matrix, but you can add the scalar matrix to a matrix. That's why it's very important to realize that these scalars we've been multiplying by vectors are really matrices. Okay, I beat that horse to death. Now what happens when we transpose A and B? Well, if we just go through and do the rule set with B and A swapped and then rearrange everything over here so we get the signs in the right order, we find out that by transposing A and B, all we end up doing is negating the cross components, the cross product. The dot product, it doesn't matter. And so we end up learning an identity here that BA is the sum of the cross and the dot products for AB, except that the A cross B is negated. The cross product is negated. And this gives us a new matrix operator that I call the matrix conjugate, where we just negate the cross components. This is similar to the complex conjugate of complex mathematics. It is analogous, I don't know if that's the right symbol, to the transpose of A and B when and only when you're using square matrices. And that's going to be all we're ever going to do anyway, so you can use the transpose here. Okay, but again, if you're doing a 3 by 3 matrix, this is a 3 by 3 matrix is going to give you a 4 by 3, and the transpose is also going to give you a 4 by 3. So using a transpose on that's going to give you the wrong answer. You got to use a matrix conjugate where you just negate the cross term. So when we transpose the vectors, all it's going to do is negate the cross products. You can see here that this one's negative, this one's positive, this one's negative. And so we can use this identity here where if we transpose BA, it's the same components as AB except that the cross product is negated. Okay, and this is shown here using this matrix conjugate, and which also be the same as the transpose of AB for square matrices. And then we can break this out because when we swap BA, it's the same thing as if you swap the cross product. It negates, be the same thing as a negative. So in other words, B cross A is the negative of A cross B is basically what we're saying, which is identical to classical cross product behavior. And again, we can apply, if you like, we can apply the transpose. Okay, it's the same thing. All it's going to do is negate, the conjugate, all it's going to do is negate all the terms in the cross product, because in the cross product, remember, all the diagonal terms are 0. All right, so this matrix conjugate, all it does is negate the cross components. It doesn't negate the main diagonal, which is the dot product. And again, the other thing we learn, another identity, is that when you do B dot A, that's the same thing as A dot B. There's no sign difference here. So when you transpose the two vectors, it doesn't affect the dot product. It only affects the cross product. That's basically this slide in a single word. Okay, so we learned something. If we sum in difference, in other words, if we sum two transposed multiplies, in other words, you have vector A times B plus vectors B times A, what's that going to tell us? Well, when you put all the values in for this, you find out this reduces to 2 times the dot product. And if we subtract the 2, we get 2 times the cross product. Okay, and you can go through the algebra there. It's pretty simple algebra. You say, well, where does this have any value to us? Well, let's introduce the new Pythagorean theorem. Remember Pythagorean theorem, we have the hypotenuse C. The length is hypotenuse C. And we want to find the length of the hypotenuse C when we know the run and the rise, which we're going to call vector A and vector B. So in vectors, all we do is say that vector C is the sum of A and B because they end up at the same location. The sum of A plus B ends up at the same location that vector C does. Now we're going to square both sides, which ends up being this. And we're going to expand this square here to be this. And then we're going to do our FOIL, remembering that the order of multiply matters. So A times B, or plus A times B, plus B times A, plus B times B. Okay, now this is a vector squared by itself becomes a scalar matrix, which we just show as A squared. There's B squared. And here we had left over with the sum of two transposed vectors. And we go back to our identity and say that AB plus BA. Oh, I forgot to put the matrix sign around that, sorry. Typo. Okay, AB plus BA is 2A dot B. So we can replace that with 2A dot B. And because A dot B is a scalar matrix, we're going to show it in regular form here, in regular dot product form rather than the matrix form, because we can do that. So now what we learn here is that if A and B are perpendicular, and we've learned from previous classes that when two vectors are perpendicular, the dot product is 0. And what do you have? You have Pythagorean Theorem. The sum of the hypotenuse is the sum of the magnitude of A squared plus B squared. But what we have now is we have a more general form of Pythagorean Theorem. I call it Q-Pythagorean Theorem to be fun, which now it doesn't matter. You now can find the length of the hypotenuse even if your vectors are not perfectly perpendicular. So this is a more general Pythagorean Theorem thanks to Q-Algebra. And here's another place where it applies, going back to Q. I'm not going to read this to you. You can pause the video, look at this yourself. This is the example we demonstrated in Q104. So let's look at this right-left multiply a little bit. Let's say we've got vector A, B times C versus, what's the difference? How can we understand what the difference is when we multiply C on the right or when we multiply C on the left? Okay, if we go through and we do the expansion like we did before and run through the rule set, okay, we're going to end up with, because now C is being multiplied from the left rather than the right. And remember what we said before, that's only going to negate the cross components. Only these are going to be negative because this is now on the other side. Okay, and you can go through the rule set and find that out yourself, that only the cross product components are going to be negated when you multiply C from the other side. Okay, therefore you can say that the left multiply of C into matrix AB is the same as the the matrix conjugate times the right multiply of C, which is more, you can also look at it as you just transpose B and A and multiply by C, which is probably the simpler way to look at it. Which, because we're always going to be using square matrices, you can use AB transpose times the right multiply of C. Okay, this way here we can turn a left multiply into a right multiply. And the reason why we like to do that is because all of the math that I wrote, or the routines I wrote before, only do right multiply. And so to support all those computer algorithms, I want to turn any left multiply into a right multiply wherever I can, because that's the tools I have. And that way I'd like to get working with one tool before I start making more specific tools to do left multiply specifically. Okay, but how do we, this is the algebraic explanation. What is the visual explanation of this? Let's go back and remember that when we have right multiply, that's like the vector coming in the top, going down the cross point network, and being shot out to the left. Okay, that's our normal right multiply that we have all the algorithms written for already. So what's this left multiply? Well, left multiply is as if you shove the vector in the left side and the result comes out the top. In other words, we're pushing the vector through the matrix in the opposite direction. Okay, and I should have put these little squares instead of triangles, so make it shown that there's that these work in both directions really. Okay, sorry to make triangles there. So these little coefficients work both ways. And so if we shove the vector C in this dimension, we're going to get a different vector coming out the top because of the way, the coefficients are going to work out. And so this is the analogy of now if you took all this and you were able to flip this guy, transpose it, flip it like this, okay, then you'd actually be flipping the input with the output. So by transposing AB, which would, flip it, you could put the C on the other side and get the same effect. Okay, there we go. We flipped it. And now, because we transposed the matrix by flipping the order of the multiply of the BA, now we can multiply C from the right side and get the same answer as if we'd multiplied C from the left side. That's the pictorial explanation. Okay, and again, I should have used little squares for these coefficients. I apologize. Okay, so now we have some Q-algebra multiplication identities under our belt. We understand a little bit more about what AB matrices are and what Q-algebra is all about. And we've also introduced Pythagorean Theorem. That's my fun name for it. In the next video, we're going to delve into Q-algebra division, left and right division, which is a little more specific than the multiplication side. And then on the video number 8, we're going to show what the AB matrix really means. We're going to show you pictorially what it really does. Then the 9th video, we're going to get into Q-algebra manipulation and rules. There's a lot of rules. Q-algebra can get very extensive. You can do everything with regular algebra you can do with Q-algebra. And because of that, we need to talk about rules, because order of multiplication matters in Q-algebra, where in a lot of regular algebra it doesn't matter. And because of that, that's why you get a lot of ambiguities with regular algebra. Q-algebra solves a lot of the ambiguities, and you get rid of a lot of the nonsense and undefined stuff you get because of the ambiguous rules of classical algebra. Okay, then we're going to get into using that new Q-algebra to develop more extensive identities that we need for ethereal mechanics. And then we're going to do some exploration of the Q-continuum. Really, what does it mean? And then that's going to include the wrap-up of this course, because that's all we need to do to go back into ethereal mechanics. There will be Q-algebra software released, and there will be instructional videos released in parallel in the support playlist. The support playlist will give you the information where and how to download the software. It'll all be free, of course. Okay, no more voodoo physics, no more voodoo mathematics, and let's get this party started.